Okay, so let's take a look at this. We're doing a titration, and whenever you're doing a titration, you're neutralizing whatever the analyte is. If you were in lab and you read the safety protocol in order to do the safety video, read that, because that scenario was based on a student X doing a titration. The major flaw to that particular scenario, and I asked in the question, why will this titration never work? And the major flaw is that the student is titrating an acid, and the student puts an acid in the titrant. So you've got an acid mixing with an acid. That'll never work because the acid will not neutralize another acid. Okay, so what you need is a base to neutralize the acid. And so that's how you do a titration, because there's a chemical reaction that takes place. So if you have an acid as a titrant and an acid as the analyte, remember the analyte is the chemical that's being analyzed. That's why it's called the analyte. It's usually the chemical in the Erlenmeyer flask. The titrant is the chemical in the burette. If you have both of them in terms of the same type of chemicals, titration won't work. Okay, you'll never neutralize one, because what's happening is that you never get to the point where the hydronium ion is wiped out by the other chemical. So just to give you that, in terms of what we have here, we have a weak acid, that's the analyte, with a strong base, that's a titrant, or a weak base that you're analyzing, and it has to be neutralized or titrated with a strong acid. It has to be opposite. So whenever you have a titration curve, whether it be an acid and a base titrated against the base, or a base titrated against the acid, what you need to remember is that there are 4 regions that you have to think about. These 4 regions are basically strategy of approach in order to solve these problems. The other thing that you should know about titration is that you're given information about both chemicals. You're given information about the analyte, you're given information about the titrant, and you're going to need to use that information to do some of the calculation. The whole idea of this titration exercise is to calculate the theoretical pH when you add some titrant into the solution. What is the pH of the solution? That's the whole exercise. And why do we do that? Because if you understand how the titration curve works, then you understand acid-base chemistry, okay? So there are 4 types of calculations that you guys are going to be doing. Let me fix my other screen here, okay? Sorry about that. I have to make sure that my other screen was clear, because when it records the Zoom, if there's something covering it, then that something is going to cover the recording as well. Anyway, there are 4 types of calculation, and you know how to do all 4 types. Okay, and so let me just introduce it to you here, and then I'll show you where each of that strategy applies in the titration curve. Okay, so you imagine an analyte. It could be hypochlorous acid, it could be hydrofluoric acid, it could be acetic acid, it could be carbonic acid, but it's going to be a weak acid, and you're titrating it against sodium hydroxide. Before you add any sodium hydroxide, you need to figure out what the pH of that acid is. You know how to solve that, because it's basically what we've been solving in chapter 16. What is the pH of a weak acid? So that's the first one. It's an equilibrium problem because it's a weak acid, okay? The second part, as soon as you add some titrant, okay, as soon as you add some titrant, a drop or 2, some of that titrant is going to react with the analyte and get neutralized, okay? Remember that when you add a titrant, it strips off the hydrogen from the acid. What's left behind is the conjugate. And the conjugate in the reaction is a product. So what you have there is that you have some products, the conjugate, and you have some unreacted acid. Guess what? You have a buffer. So as soon as you add some titrant, you can solve that problem, the pH of that solution, via the Henderson-Hasselbalch equation. So you know how to do that because we talked about that last time. And that's a handy equation. The next part is you get to the point where you've neutralized all the acid. Okay, you've added enough titrant so that the hydroxide is equal to the acid moles. And so you don't have any more acid left behind, the original acid left behind, because it's been completely neutralized by the titrant because you've reached the equivalence point. Guess what? The moles of acid that you originally have is now the moles of the conjugate because everything gets converted. The concentration is not the same because remember, the concentration is the moles divided by the volume. The volume has changed. It's now equal to the volume of the analyte that you have plus the volume of the titrant that you've introduced. So the concentration is going to be different from the original analyte that you analyze. But the moles are the same. The moles are the same. You got to get in your mind there's a difference between the moles and the concentration. The moles tells you the individual atom, the individual molecule. The concentration tells you the moles or the atoms in the volume it occupies. They are certainly different. Okay. Now, if you have a volume of 1 liter, then they're going to be equal because you're dividing it by 1, but the units are different. So you got to get that into your mind that moles and molarity are basically different because one is a concentration unit, the other one is an individual particle unit. Okay. But when you get to the equivalence point, all the analyte gets converted over to the conjugate. And you know how to solve that because that's just a salt. That's hydrolysis. What you need to realize is that the conjugate now is going to react with water. Why does it react with water? Because it's the conjugate of a weak acid. By definition, that base is going to react with water and pull some water, pull some hydrogen back so that it converts over to the its conjugate acid. But you guys know how to solve that because that's the same type of strategy that you use when you're solving for salts. Remember salts, it breaks up into its ions and the ions react with water. It's called hydrolysis. Well, in this particular case, you have the acid, but now it breaks up into its anion because that's the only chemical that's going to be remain because its hydrogen's been stripped. It's been converted with water to water by the titrant. Now that chemical, the conjugate, is going to react with water. And in this particular case, it's going to form hydroxide. So you need a Kb. And then you're going to calculate a POH. And then you need to convert that to pH. So that's what happens at the equivalence point. It's not difficult, but remember, when you have a problem like a titration, it's multiple steps, and that's always difficult in general for students. It seems like most students can solve maybe 1 or 2 steps, but when it comes to more than that, it becomes complicated. But just think of these problems as individual steps, and you'll be able to easily make it through. The last part is the excess titrant. What happens now is that you've neutralized all the acid. They convert over to the conjugate. Because the conjugate is a weak base, it's not going to form very much hydroxide. Okay? It's going to form hydroxide based on the Kb of that base. But the excess hydroxide that goes unreacted, now that's the chemical you have to watch for because the excess hydroxide in the volume that it sits in now tells you the concentration of the hydroxide. If you have the concentration of the hydroxide, you can basically calculate the POH, which will give you the pH. So these types of problems that we're talking about in these types of questions, you guys already know how to do. It's just a matter of stringing it together and working each problem one at a time so that methodically, so that you don't confuse. you don't get confused. You will definitely see one of these in your midterm. You need to practice, especially for those of you in lab. The activity is really good practice for you to do that. And I'll show you the shortcut equations to use so that it doesn't take you a whole lot of time in this discussion. Okay, so that's basically what's going on. Here you've got an equilibrium problem. Here in blue, you have the buffer problem, the Henderson-Hasselbalch equation. At the equivalence point, when the moles of the acid and the moles of the base are equal, this is the hydrolysis. It's like solving for salts, the pH of salts. And here, it's basically stoichiometry. That's the four regions that you guys are going to be calculating, that you guys are going to be approaching in these types of problems. Okay, so that's what we have. Now, the beginning of a problem is critical. And the reason why it's critical is because if you mess up in the beginning, your pH is all going to be off. Okay, and I don't mean to fool you. I just mean to test your ability to do chemistry. And sometimes what I will do is I will take that base and not give you a mono basic chemical like potassium hydroxide. For every one potassium hydroxide, you get one hydroxide. But if I give you a chemical like calcium hydroxide, and this is not to fool you, it's only to make sure that you understand the chemistry, to visualize the chemistry first. Okay, because you'll see things like this in the ACS exam. You got to remember, for if I've got a 1 molar calcium hydroxide solution, my hydroxide is 2 molar. Why? Because for every 1 calcium hydroxide, I have 2 hydroxide. You got to be able to see that because it's back to the chemistry, it's back to the fundamentals. Okay, you got to know what systems you have so that you can start off your problem correctly. So I just want to throw that out there because you probably might see some homework question like that. Don't get fooled. Look at the chemical you have. Don't always assume it's going to be a strong base. But will that strong base be 1-on-1 with the hydroxide, or will it be 2-in-1? There's no such thing as 3-in-1. Okay, it's 2-to-1 or 1-on-1. So let me go ahead and erase that. So
I was
titration
gonna
of a
ask.
weak. There was a question.
Yeah, I was gonna ask if you're gonna give an example of the four ways to solve
Yeah, I
weak
am.
state.
I'm going to do that right now. Okay. So yeah, you're reading my mind. But first, we've got to set this up. We've got to make sure that we understand, because what you need to realize is how much do I need to add to hit these markers that the question is asking. And that generally means that you need some information in the beginning. So here's the question. You have a titration. You have to recognize this is a weak acid. And how do you recognize that? Because it's not one of our 7. You should recognize this, that this is a strong base because it's got a hydroxide. Alkali, that's group 1, or heavy group 2. Heavy group 2 means calcium, strontium, barium. Group 2 metals that have higher atomic weight than calcium. That's heavy group 2. Anyway, potassium hydroxide is a very strong base. Okay, generate a titration curve between 0%. So 0% just means that 0 titrant was added. 50% means that 50% was added so that you're 50% to the equivalence point. 95% means that enough titrant, potassium hydroxide, has been added so that you're 95% to the equivalence point. 100% means that you're at the equivalence point, and 105% means that enough volume has been added that you're 105% past the equivalence point. Now, the key here is that you need to focus in on that 100%. Why is that you need to focus in on that? Because that's where the moles of the acid is equal to the moles of the base. Okay, that's your equivalence point. So if you know the moles of your base or the moles of your acid, you can figure out how much volume of base you need in order to get you that same mole. That's why you have to focus in on that 100%. Ignore the others. Focus in on that 100% because you know the chemistry there. Most of the acid, most of the base are equal. Okay. Then I give you information. I tell you about the analyte. So the analyte, we have 10 mils. So basically, we have a Erlenmeyer flask. We've got 10 mils in here. Now, the 10 mils, the amount of acid in that 10 mils is fixed. The moles of that acid is fixed. Adding water in here does nothing in terms of the concentration. I mean, nothing in terms of the moles. So when we do a titration, we usually rinse the side with water because the critical point is the equivalence point and it's only based on moles. So 10 milliliters and our concentration is zero point 0.4. So right away, you know, this is moles per liter. You know how many moles of the acid you have to analyze. And generally, that's going to be given to you. Okay, you're going to be given the concentration of the analyte, you're going to be given the volume that you're going to be titrating. And here I'm going to introduce you to a new unit called millimoles. And the reason why we need to use millimoles is because our titration uses milliliters. If you convert this to liters, you're going to be ending up converting it back to, you're going to be, remember the amount of titrant you're adding is milliliters as well. Well, it just introduces two calculations that you don't really need to do because they'll cancel out at the end. So by knowing that milliliters is there, when you do this multiplication, that would be 4. Okay, that would be 4 times 10 to the minus 3 moles. But why do 4 times 10 to the minus 3 moles when you can just say 4.0 millimoles? Okay, the milli tells you already it's 10 to 1 times 10 to the minus 3. You want to use millimoles or milli because you're dealing with milliliters. So this is going to be 4.0 millimoles. And look what happens here. You have the same amount, same concentration of potassium hydroxide, zero point 0.4. So it's a no-brainer. You're going to need 10 mils of potassium hydroxide in order to reach 4 millimoles as well, because the concentration of the acid and the base are equal. Okay? You don't even have to do the calculation. It's going to be 10 mils. So this right here is 10 mils. And then you can calculate the rest. If you take 10 and multiply it by 0.95, you get 9.5 milliliters for your 95%. If you take 10 and multiply it by 0.5, you get 5 mils. Okay, and then of course 0, 0, and then 105 would be 10.5 milliliters. That's how you play that game in the beginning, because you need to figure out the pH at each of these volumes. Okay, now suppose this wasn't 0.4. Let's say that this was, say, let's give you a weird number, 0.50 milliliters. Well, I can simply, sorry, 0.5 molar. I can simply take this 4.0 millimoles and do this. I'm going to take 0.50 moles per liter. And if I do that, then I can calculate the volume that I will need to reach the equivalence point. Okay? Because remember, in this particular case, the moles of the acid that you're titrating has to be equal to the moles of the base. So you just use that number because they're going to be equal at the equivalence point. Then all you've got to do is divide by the concentration of that base to figure out the volume you will need to reach the equivalence point. And so if you take 4 and you divide it by 5, let me get my calculator, 0.5 that is, what you get is 8. Okay, 8.0 milliliters. And notice I didn't have to convert it to liters. I mean, I could have gotten 0.008 liters if I did the conversion. But why do the conversion? Your answer here will be in milliliters. And that makes sense, doesn't it? Because if my If my concentration of my acid is zero point 0.4 and I have 10, and my base is much stronger, okay, by 20%, then I would need a lower volume to reach the equivalence point. 8 milliliters is a lower volume than 10. So use your chemistry knowledge to make sure that you know that you're in the right ballpark. Of course, it's going to take a lower volume because you have a higher concentration of your analate. So this is critical in the beginning because you need to know what volume of base in order to calculate the pH. You need to know what volume of base so you can calculate the hydroxide ion concentration and react it with the acid. If you can't set it up in the beginning like this, then you're going to get lost. You're going to be using the wrong volume, and then you're not going to be hitting the pH points. Okay, so let me just clear this out. So this is basically the math right here that I'm showing you. Okay, and based on that, and you guys could have done this without even doing the math because the concentration are the same. 100% is 10 milliliters. Okay, so the other thing that you need is the Ka of that acid. Since you know the identity, you could look up the Ka, and you also need the pKa. Reason why you need the pKa is because it's going to be helpful in the Henderson-Hasselbalch equation. Remember, the pKa is equal to negative log of the Ka value. So if I take 3.5 times 10 to minus 8, take the log of that, and take the negative of that number, I get 7.46. Double check. So that's the first part of this problem. Now let's look at what happens when we have 0% titrant added. That's just a weak acid. Okay, that's just a weak acid. What we have is hypochlorous acid. I tell you the concentration is 0.4. Hey, go straight to this equation. Remember what I said? The Ka was 3.5 times 10 to minus 8. We said that the concentration of the acid was 0.4. Okay, I mean, you could do the ice table if you want, and it'll get you to the same place. Or you can do this. And if I do this calculation, 0.4, 3.5 to the 8 negative, I multiply that out and take the square root of that. Then I get my hydrogen ion concentration is 1.18 times 10 to the minus 4 molar. And my pH of that particular solution, if I take the log of that and then take the negative of that, is 3.93. Took me less than a minute to calculate that. That's why you got to know what strategy you have so that you could take the direct route rather than the long route. And that's what you see right here. Let me clear this up. Remember that value, it's in my calculator, 3.93. Here I sort of walk you through the ice table. Here I show you what's going on. It's exactly what we got. It's exactly what we got. Okay. So that's our first point. That's our first point. The second part of this is we're now going to do 50%. 50%, let me give you a big hint, okay? But a lot of you are going to make this mistake. Let me make sure that you do not make this mistake in your midterm, okay? 50% is not the equivalence point. It's halfway to the equivalence point. It's halfway. You guys know that, okay? You know that, but it won't register, especially when your IQ drops 30 points during an exam. But write it down somewhere. 50% is when half the original acid gets converted to its conjugate. Guess what? These two are equal. The acid, after, because look what happens. You have 4 millimoles of acid in the beginning, and you're introducing hydroxide, and you're only introducing half of the 4, 2 millimoles. That's 50%. Take 5 mils and multiply it by 0.4, you get 2 millimoles. Guess what? you're going to get the conjugate of that acid, OCl minus, and water. Water plays no role in the chemistry. But what happens is that this is the limiting reagent. Half of it, this is the stoichiometry. This is what we start. This is what reacts. That's where the SRF table comes in. Half of it's going to react. Of course, this is the limiting reagent. So this is going to be 0. But the half that react now converts over to this right here. It forms the conjugate. Okay, it forms the conjugate. Whatever reacts here is what forms there. And then finish. This will be 2 millimoles. That's where the SRF table comes in. This is 2 millimoles. This is a buffer situation. In a buffer situation, you use the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of the base. Remember, it's concentration of the base. The base is 2 millimoles over, remember we started out with 10 milliliters of the analate, and then we're introducing 5, so that's over 15 milliliters over the conjugate acid. And this is 2 millimoles over 15 because it's in the same Erlenmeyer flask. An interesting thing happens that you should observe. The volumes are equal, so they cancel out. So you don't even need to calculate the concentration when you use the Henderson-Hasselbalch equation because the volumes cancel out. All you need really are the moles. All you need are the moles. And guess what? The log of 2 over 2, well, the log of 1 goes to 0. So the pH equals the pKa. But that's only true at halfway to the equivalence point. So whenever you see that in a problem, it's free points. Okay, it's free points. Not at the equivalence point, but halfway to the equivalence point, the pH equals the pKa. Free points. If the question is worth 20 points and each part of this is worth 5 points, that's free 5 points because you don't have to do any calculation. You can just say that the pH is equal to, what did we say it was? 7.63, okay? Let me write that down somewhere. So 7.46, that's the pH at halfway to the equivalence point. It's 3 points. So don't even bother. Don't even bother lifting your calculator on that because the pH is going to be equal to the pKa. And that's because these two are equal. These two are equal. It cancels out in the Henderson-Hasselbalch equation. That's what we got. This is basically the Henderson-Hasselbalch equation in action. 50%, not at the 100% level, okay? When you're 50% of the titration. Yeah, talk to me about that question towards the end, okay? Yeah, you can certainly do that. The study guide's basically the sample exams that I have in the website. So let's take
Those
a
are
look at
suitable for review for the midterm.
what was that? Yeah,
Those exams are suitable. Okay.
those are certainly suitable for the midterm. Let's take a look at 95%. Let's take a look at 95%. 95%, again, you're still in the buffer. Why? Because you haven't reached the equivalence point. Okay, you haven't reached the equivalence point. So 95%, remember, is 9.5 mils. If you multiply 9.5 by 0.4, okay, 9.5 by 0.4, that's the number of moles, millimoles of hydroxide you have. So 9.5 times 0.4 is going to be 3.8. So again, we have our hypochlorous acid, we've got our hydroxide, it's going to form its conjugate. So the first part is always stoichiometry, start. This is 4. We're always going back to as if the problem wasn't a continuous from last time. You're not going to use the answer of HOCl from last time. You're going to look at the original HOCl because now it's being reacted with 3.8 millimoles of hydroxide. Okay, you gotta put the original here, not the answer from the last question, because you gotta start each analysis as if it was fresh. So take a look. This is still stoichiometry, the first part. That's why we have SR, start, react, minus 3.8. This is going to be plus 3.8. All the base takes 3.8 HOCl, takes the hydrogen from 3.8 millimoles, and then that 3.8 millimoles that reacts now converts over to its conjugate. That's why these two are always equal. Okay, because the hydroxide will convert that many acid into its conjugate. What remains now, finish, is 0.2 millimoles. And this will be 3.8. Hey, this is still a buffer situation. This is still a buffer. Let's just take the pH equals the pKa plus the log. Remember, it's the base, 3.8 divided by the volume. But the volumes are going to be the same for both numerator and denominator. 0.2 divided by the volume. I don't even have to put the volume here. I know what this is. I've got the pH of the solution. Remember, this is not at the equivalence point. This is still the buffer region. So let's see how that's done when I do this clearly. See, it's 3.8, 3.8, 0.2, 3.8. Yes, I converted to concentration because that essentially is what's happening in the solution. But I didn't need to use 0.195 and 1.03 times 10 to the minus 2. In fact, when you do that quotient, you still get the same number as if you were taking 3.8 and dividing it by 0.2. The ratios are still the same. So that's exactly what happens here. Okay, this is the long way again. This is the long way showing the ice table. I always want to show you the long way because that's the fundamentals. And then this right here is the Henderson-Hasselbalch equation. Yeah, I used 0.195 and 1.03 times 10 to the minus 2, but I could have easily used 3.8 and 0.2. And if you do that, what you will see is that it gives you the same number. Okay, so these are the little things that you sort of catch when you do a lot of these problems. And so this is 7.46, and if you do that, it's 8.74. It's going to be higher than the previous one. Your pH is steadily going up. If all of a sudden your pH drops, you've made a mistake. And probably it drops because you're actually plotting pOH and not pH. Okay, the titration curve will always go steadily up. It never abruptly drops. Okay, so this will be, yeah, ask me that question again in towards the end of class. Okay, because I don't want to disrupt my train of thought here. So that's essentially what happens. We're not at the equivalence point yet. Okay, we're not at the equivalence point yet. We're still in the buffer. You're in the buffer when you have the acid and its conjugate in the same solution via a chemical reaction or via introducing it via the start of the reaction. Okay. Now, some of you are going to be confused because you're going to think, okay, I've got some acid. If I just start my acid and it breaks over to its conjugate. So it looks like you have a buffer situation because you have got some concentration of your conjugate and you've got some concentration of your original acid. That's not a buffer because that reaction, that chemistry occurred via the natural chemical reaction. This right here, once we get into our equilibrium table, our ice table, you have in the initial line both chemicals present. That is a common ion problem. A common ion problem is a buffer problem. Common ion and buffers are going to be the same. Common ion would be the generic umbrella term. Buffers are for acid-base chemistry. Okay, so let's take a look at what happens when we reach the equivalence point. At the equivalence point, all that acid, all that 4 millimoles of acid has now converted to 4 millimoles of conjugate base. Why? Because at the equivalence point, there are equal amount of base and acid. Because there are equal and you have a strong base there, the strong base is going to annihilate all that acid. It's going to demand all that hydrogen from the acid, because that's who run the show. All the acid without its hydrogen now becomes its conjugate. Well, that's going to be sitting in water now. That's going to be sitting in water. And in water, because it's a weak base, it's going to react with water. And it's going to remove that hydrogen from water. And you're going to get a basic solution. You're going to get a basic solution. That's the chemistry that occurs. So this, because that's the reaction that occurs, notice that tells you it's a KB. That right there tells you it's a KB problem. So how do you calculate KB? Well, if you know Ka, pKa plus pKb equals pKw. And this is generally 14 at 25 degrees. We already said that this was about 7.46. So just take 14 and subtract 7.46 from that, and you got the pKb. Why do you need that? Because you have a KB problem. You've got a KB problem. You got to understand the chemistry. So let me go ahead and clear this for you. And let me show you again. You just need to do this. It's going to be 0.4 millimoles. The volume now, because remember, whenever you're doing equilibrium, you have to use molar concentration. You can't just use 0.4 millimoles. The total volume now is the 10 that you originally had plus the 10 titrant that you add. That'll be 20 milliliters. See how the millis cancel? That's why I like millimoles. Because when you have 4 millimoles, it's 4 millimoles, not 0.4. It's 4 millimoles. When you have 4 millimoles and dividing it by 4 milliliters, the millis cancel, and it's just like 4 over 20. In this particular case, that'll be the concentration. And then you multiply this by the Kb. And that'll be your hydroxide ion concentration, which will lead to the POH, which leads to the pH. You guys know how to do this. You do. We covered it in the last section. You need to practice. So let me show you how that works out in the notes. All of this is annihilated. They're equal. And what you get is 4 millimoles of the conjugate that forms. In the total volume, 4 millimoles divided by 20 milliliters. See here, I'm keeping count of the volume because it's always changing in each problem. Well, that's 0.2 molar. So I can do the ice table and use the 0.2. This is a Kb and solve that. Or I can just do this equation. This equation right here, that hydroxide is equal to 0.2 times, what did we say Kb was? We said that Kb was 2.86 times 10 to the minus 7. Okay, that's 2.86 times 10 to the minus 7. Take the square root of that, and that's your hydroxide ion concentration. This is the other way to calculate Kb. Kw over Ka equals Kb, or pKb equals 14 minus pKa. Those are two equations that we covered way back in the beginning of this particular section. When you do this, you get a POH of 3.62. So imagine if you were graphing this. What you would see is you would see something that looks like that, and then all of a sudden your points drop to 3.62. You know that's wrong, because the curve will not dramatically just drop. That's a POH. You got to subtract. You got to take that number away from 14, and you get 10.38, and it's going to be up here. It's going to be up there. So this is what it looks like when you graph that. It's not going to be down here. It's not going to be down here where it drops down. You know you made a mistake if it drops down like that. How do we know the total volume? You know how much you started with. That's described in the titration. You know that you had 10. The equivalence point is when you add 10 milliliters of titrant. That's 100%. 10 plus 10 is 20. That's your total volume. What was the total volume at 95%? It's 10 that you originally had plus 9.5 that you've introduced. So it's 19.5. What is the total at 50%? It's 10 that you originally have plus the 5 that you've added. That's 15. What's the total at 105%? It's 10 what you already have plus the 10.5 that you're going to add. That's 20.5. So you just have to keep that running count in your mind and understand the chemistry that's going on. At the equivalence point, you're introducing 10 milliliters of titrant. Now the total volume has changed to 20. Okay. Pay attention to this number because this is the concentration of the base that you have. That's concentration of base, and look how much hydroxide it introduces. It only introduces 2.39 times 10 to the minus 4. Why is that number important? Because you're going to see in the next step how insignificant that value is compared to the excess hydroxide that you've added. So we're good at the equivalence point. This is equivalence point, hydrolysis. Look what happens when we're past the equivalence point. We're now at 105%. Again, you set up your reaction table. We still have 4 here, but now 10.5 times 0.4 is 4.2 millimoles. That's going to be in excess. 105% equals 10.5 milliliters of titrant. 10.5 milliliters of hydroxide times 0.400 moles per liter. Okay, that gets you 4.2 millimoles. Just in case you forgot. 4.2 is in excess. By how much? 0.2. Okay, by how much? 0.2. So that's what you see right here. The amount excess is 0.2. That's the amount of hydroxide that went unreacted. If I just take that excess and divide by the total volume, 0.2 millimoles, remember the total volume now is 20.5 milliliters. That's the concentration of my hydroxide. That's the concentration of my hydroxide. And if I do that, if I take 0.2 and divide it by 20.5, I get 9.76 times 10 to the minus 3. That actually is going to be the hydroxide ion concentration. You don't have to do anything further. You just take the negative log of that number, and when I do that, I come up with 2.01, and if that would be the POH, and the pH on that would be, I subtract 14, and that would be 11.99, approximately 12, approximately 12. Now you might say, well, doesn't this conjugate right here going to give you hydroxide? And won't that hydroxide add to this hydroxide that was in excess? Go back to the original problem. I mean, the previous problem. This is 0.2. That's how much conjugate was formed. And remember, the 0.2 only gave us 2.39 times 10 to the minus 4 hydroxide. Look at this problem. It's 0.195. Why is that number lower, even though you're further past the equivalence point? Because that 0.2 is divided by a greater volume. The new volume is now 20.5. At the equivalence point, the volume was 20. At 105%, you're at 10.5. So 4 millimoles divided by 20.5 is going to be a smaller number. So right away, you know that this number can't be any higher than what was that? Keep forgetting. Can't be any higher than 2.39 times 10 to the minus 4. It's going to be smaller, in fact. But let's just say that this is 2.39 times 10 to the minus 4. And that's the hydroxide that is introduced to the hydroxide in excess. If we add those two up, I'm going to take 9.76 to the 3 negative, and I'm going to add 2.39 to the 4 negative. When I add that up, it's still 9.99 times 10 to the minus 3. It really didn't change that number very much. And when I take the negative log of that, this now becomes 2. And the pH of the solution is still about 12. It doesn't add very much to the hydroxide because your strong base is going to be what's going to affect the hydroxide ion concentration. So let me just show you that, okay? And what's going on here, I'm basically taking the hydroxide excess and I'm calculating the hydroxide ion concentration and I'm converting it to POH and then pH. It's about 12, okay? 11.9999 is about 12. Here's the correction when I think about how much of that conjugate base is adding to the total hydroxide ion concentration. It adds very little amount, actually. Okay, this is actually a quadratic. And I'm not going to ask you to calculate the amount that the conjugate is asking because I really just want to know the pH of the solution. And if I add that to the original, to this value right here, what happens is that it basically doesn't change. The amount of hydroxide, which doesn't change the POH, which doesn't change the pH. So whenever you're past the equivalence point, the shortcut is just figure out how much extra hydroxide you have in the new total volume, calculate that concentration, that'll get you your pH. Okay, so there's 4 problems. These are 4 problems, but they're all very doable, and you've got to make sure that you're applying the correct strategy for these 4 different problems. Okay, this is 11.99, and I summarize that in this neat table. Okay, I didn't do this in the past, but I came to realize that you guys really need this. Number 1, it's basically just an acid. This equation right here is just H plus equals the square root of the acid concentration initial times Ka, the square root of that. That's what this equation is right here. This equation in part 2, so this is part 1 right here. When you add 0, part 2 is your buffer. That's your buffer right there, using the Henderson-Hasselbalch equation. Pay close attention at the 50% mark, because at the 50% mark, that cancels out and your pH equals your pKa. Part 3, that's this right here. You've got your hydrolysis. All your acid converts over to its conjugate base. It now becomes a Kb problem. Figure out what the Kb is and then use this equation. Hydroxide is equal to the square root of your base concentration times Kb. That's what this equation is right here. And then finally, the very last, just figure out this right here is the excess hydroxide that didn't react. So you're taking the hydroxide that you introduced minus the limiting reagent. That'll give you the moles of the hydroxide that went unreacted over the total volume. You have to divide by the total volume because you need the concentration. Once you have the concentration, you've got your POH concentration. You get the POH, and then you convert that to pH. So these are nice, handy formulas, so you know how to solve these problems directly. Okay? Practice, practice, practice so that you are comfortable. But it's not difficult. It's basically what you guys already learned in chapter 16, and then the common ion, the buffer that you were introduced last lecture. That's what this is. Okay. Now let me just finish up this section because I want to introduce you to some traits of titration curve. Whenever you have a strong acid, strong base, it'll always start low. That means that your analyte's a strong acid because you don't get a low enough pH unless all the acid dissociates. Okay, weak acid, even if you have a 1 molar concentration, you're going to get pH of about above 3. 10 to the minus 3 is going to give you about 0.001 molar hydronium ion, even if you begin with a 1 molar weak acid. It's not going to be a very uh, it's not going to be a very low pH. It's going to be somewhat high pH, 3 or above. So you know you have a weak acid. I know this is a strong acid because it's way below 1. Okay. Um, and then the other thing that I notice is that if I take this and I take this and I look at the halfway point, it goes exactly through 7. And the reason why the pH at the equivalence point is 7 is because imagine strong acid, strong base. They annihilate each other. Their conjugate doesn't do anything because by definition, that's what strong acid, strong base does. Their conjugate does no chemistry. What's left in that solution? Just water. What's the pH of water? 7 at 25 degrees. That's why this thing has to go through 7 at the equivalence point, because you have neither excess acid or excess base. The chemistry is based on water. The pH of water at 25 degrees is 7. It has to go through 7. And then it goes to the top, and look at how high that pH is. Here you have excess titrant, excess base that you're adding. The fact that it's above 12 means it's a strong base. So when you have a titration curve like this, especially pay attention to the equivalence point. It's symmetric, strong acid, strong base situation. Strong base, strong acid would look like this. It would do this right here. Okay, it would be the reverse. Let me change color of what you see right there. It would still go through 7 as well. Okay. Remember, you start out high because it's a base. So the pH of a base will be high, and then you end up low because you're adding excess acid. This is the features of a weak acid, weak base. And this is the strong chemical right here. It starts high. What happens is that you initially go up, but then it plateaus out. That's your buffer region right there. That's your buffer region right there. And then it hits the equivalence point. And notice that the equivalence point is above 7. Why? Because the conjugate is going to produce hydroxide. So the pH at the equivalence point is going to be above 7. If you're titrating a weak acid, the conjugate now is running the show. It's going to be above 7. And then here you're going to end up, because you're mostly titrant there, it's going to be in the high value. If this was opposite, you'd see something like this. Oops. Yeah, it'll be something like this. Okay, where you start lower than 12, maybe at about 11, you get into the buffer region. The pH now is going to be below 7. Why? Because you're titrating a weak base. The conjugate of a weak base is going to be a weak acid. It's going, at the equivalence point, that acid is going to produce hydronium. That's why at the equivalence point for that type of curve, your pH is going to be below 7. And then of course, since you're adding a strong acid, it's going to end up low. So it's going to look like that. Okay, let me clear that up and show you again what it should look like. It should look like this. You're going to start out low. It's going to plateau out in the buffer. It's going to hit the equivalence point. It's going to be lower than 7. That is the equivalent point. It's going to be lower than 7. Let me clear that. It's going to look like this. And then it'll end up like that. So the equivalence point is going to be over here somewhere around 5 or 4.8. That would be the titration of a weak base with a strong acid. This is a good curve to know. I usually have a question like this in an exam. I give you a titration curve like that, and I ask you, what is the pKa of the, or even the Ka of, say, these are all The analytes are all acid. Why? Because they all start below 7. The titrant, of course, is going to be a base because they're steadily increasing. But if I ask you, what is the Ka of, say, acid D? So look at the curve for acid D. 50 milliliters is the equivalence point. 25 milliliters is halfway. All I got to do is read the pH there. That's the pKa. So that pKa at halfway is about 4. So the Ka is 1 times 10 minus 4. For acid B, well, this is, all of these have the same equivalence point. They're all hitting the equivalent point at 50. Halfway to that, it's all 25. So if I just read the pH for all of these at the halfway point, I can get the pKa. And then from the pKa, I can get the Ka. Okay. So that's what I wanted to illustrate in this curve. This right here is a titration of, again, a weak base with an acid. You have a buffer region there. It's exactly the same strategy you would apply when you solve a weak acid with a strong base. This now is a weak base. That's what you're analyzing with a strong acid. So weak base means that your pH will be high, but not like above 12, won't be 13, definitely not 14. It drops down to the buffer region. Buffer region really should start here to right before its equivalent point. That would be my buffer region. Okay. This now is below 7 because the conjugate of a weak base is a weak acid. And if that's all that you have in solution, the weak acid, it's going to produce hydronium. Therefore, the pH is going to be below, and then we end up at a very low pH because you're adding excess acid. Okay. And then this right here, you know, it's a polyprotic system because you got several equivalence points. You got an equivalent point here, and you've got an equivalent point here. You're basically removing 2 hydrogens from this chemical. Okay. When you remove the first hydrogen, the pH changes dramatically. The pH changes dramatically. That's the pH change. When you remove the second hydrogen, the pH again changes dramatically. But you know that this is a polyprotic system because you can see 2 inflection points. If you can see 3 inflection points, it's a triprotic system. Okay. And you could probably calculate the Kas because if this is the equivalent point for the first one, halfway to that, that'll be the pKa1. If this is the equivalent point for the second one, okay, so we're going from here to here, halfway to that, so we have to look at this region right here. That's your pKa2. Don't take, sorry, I labeled that incorrectly. Erase that. This is your equivalent point right here. That's at 80. Don't take 80 and divide it by 2. You'd be back here at 40. That's not the case. You need to take where you started off last time when everything was neutralized, when all the hydrogen has been ripped off. Remember, this is a polyprotic system. There's 2 hydrogens that come off. When the first hydrogen is completely ripped off, where does that start? It starts right here at the equivalence point, the first equivalence point. At that point, all you have is, so here we're having H2A. Here we have HA minus. All the hydrogen has been stripped off. The first hydrogen has been stripped off. And this from here to here is this right here. The second hydrogen is coming off. So this is the equivalence point halfway. From here to here, from here to here is going to be 60. So if you read the pH at 60, that's pKa2. So this again is the polybasic system. You guys can do that, and then you should recognize the shape of these things. That's generally what I have for you guys for today.